Welcome back from spring break, and welcome to the world of online learning. So, you've heard that saying, keep calm, and that gets completed lots of different ways. For us, it's going to be keep calm and keep learning the discrete math we need to know. I just wanted to talk with you a bit first about the general plan for the rest of the semester, but we'll actually do some new material today too. You are expected to remain available for our regularly scheduled class time. So this may be a problem for some of you. I recognize that you may have family members who are having to work remotely and who need all the internet or maybe the only computer in the house, but do your best to keep that time open. You can still participate in class with nothing more than a cell phone. So yeah. I'm going to be posting video lectures to Blackboard like this one, but these will go up in advance of class time, at least 24 hours, possibly more if I can get a little ahead of the curve. And that way you can work asynchronously for the most part. In fact, I'm going to encourage people to work asynchronously. That is, have already watched the video before class starts so that we can spend class time working on worksheets and other activities. I already said that. Watch the video before class. We'll mostly be meeting, quote-unquote, meeting on WebEx. You'll receive an email with a link for how to join the meeting well before class is to begin. Probably about the same time I launch out the video to you. I'll send an email with a link to that, as well as a link to the WebEx meeting. You should be able to join these WebEx meetings like 5 to 10 minutes in advance. Oh, let me mention one little piece of, politeness, I suppose. You'll typically join the meeting already muted. I'll set things up like that. But you'll want to unmute yourself if you need to ask a question or whatever. Just, remember to mute yourself back off so that we don't get a really confused sound stream. The other thing that's really helpful is if everybody has headsets or earbuds or something so that you don't end up creating audio feedback through the network, which can sound really strange. So yeah, if you have a headset or a set of nice earbuds with a mic, that would be awesome. Mostly the class time will be we'll deal with completing worksheets, which I will make available via Blackboard, and you'll submit them via Blackboard. So that should be fairly standard for everybody. The WebEx stuff is great for group meetings, but when I want to meet one-on-one with somebody, like in office hours, I'll be using Microsoft Teams. My office hours will remain the same. I'll probably, just because of the awkwardness of the situation, I'll probably try to extend those hours in the coming weeks, but for now just count on being the same. And I accidentally clicked and advanced the slide. Quizzes, yes, those will happen on Blackboard as well. So let's talk a little about the tech we're going to need to deal with. Pretty much everything we'll do you can do on a smartphone, so that's good. Of course, a tablet or a laptop will make things easier, but it's not necessary. If you don't have home internet access, this is going to be a real problem for you because the online learning stuff is going to require a fair amount of data, and it probably will chew through whatever your data plan is. So if you're in that boat, I recommend that you just switch up to the unlimited data plans. It's only for a couple of months, and that's probably the cheapest way. Yeah. So the main tools we'll be using are Blackboard, WebEx, and Teams, which I've already mentioned. Also, you'll need to put a scanning app on your phone so that you can upload things to me. A couple of recommendations I've had are for Genius Scan, which I've tried out and it works great, and Scannable, which seems to be only a Macintosh, iMac, or iPhone app. But if you have other recommendations, like it says, please put those into the chat room on Blackboard. That's actually something else I should mention. That chat room will be a great place for you to communicate both with me and with one another about ideas you have. In fact, anything that comes up that you think we could be doing better or smarter. Don't be shy about sharing your thoughts. The video lectures are usually going to be in the format you're looking at right now. I'll have slides, but we'll transition back and forth between the slides and this view of my desktop. I've got a couple of webcams going so you can see my smiling face, but also I can come over on this other webcam and write things, make drawings for you, so it's the equivalent of a whiteboard. Occasionally I've also got a setup where I'm actually standing in front of a whiteboard and I can just capture those sort of videos, but we'll see how different occasions will require different tools. I guess, for instance, today I'll probably be showing you a view of a graphing calculator on that webcam. Anyway, before we go too much farther, I want to splice in a little video I created about showing you how to capture things on your cell phone and upload them to Blackboard. So here goes with that. Hi, so in order to submit materials to me, and you'll do that through Blackboard, but you're going to need to have the facility to create scans of objects. And there's several apps for your cell phone that'll do that. I've got this one loaded called Genius Scan, which someone recommended to me. I've also heard nice things about Scannable, but I think that may be just an iPhone or iPad app. In any case, I couldn't find it for the Android. So before I show you the app, let me point out how your uploading of things is probably going to proceed. If you've got a printer, you can just print out the assessment. I'll post these things so that they become revealed to you just at the time the quiz begins. But you can print out the item and fill it out as you normally would, right? And then scan that. If you don't have access to a printer, then you could do something more like this, where you have just a single page, well, however much paper it takes, but you don't need to have the printer. Just clearly number the objects or the items on the assessment. Tell me the name of the assessment at the top and make sure to sign it, or if your handwriting is as illegible as mine, you can print your name there. Okay, so I'm going to illustrate scanning by doing the one that's a 2-page document. I think that'll be a good idea because you need to know how to do a 2-page document. It's not rocket science. You'll be fine with this. So open your app, and this one has a camera icon, which sort of makes sense. You just want to try to square up your view and fit the thing to a nice rectangle. Did you see that highlighting around the thing that made a circuit of it? Oh, look at that. It included just part of my table surface there, so that's probably not one I want to save. Let's see if we can do that a second time and get a better result. That's better. So to get the second page, set that up so that you can see it well. You're going to, now by the way, notice the camera icon has become a plus sign. Whoops, what did I do? Click the plus sign. You want to scan it, not import from a file. And same trick. And now we've got a 2-page document. These are the 2 pages. Please rename the document so that its name is not just a date stamp, or date and a time stamp. So, whoops. Put your name, or if you have a very long name, put enough letters of it that I'll recognize you. And try to spell your name right. What the hell did I do? Okay. And then let's switch over and look at Blackboard. Now I should already have Blackboard rolling. I'm going to readjust the tripod so that I can work two-handed. Give me 1 second here. Well, that should be good. Hopefully you can see that pretty clearly. So open up Blackboard. Now I don't actually have a quiz for you guys at the moment, but I'll illustrate by submitting it to the that online activity I gave. I gave you last week or the week before spring break. So where are we? Spring 2020. Excuse me. Okay, I'm going to put it in student preview mode. So this is me pretending to be a student. But you'll have a name for the activity. Just click into that. And when you go to submit something, it gives you two options. You can do a written submission in a text box on here. Please don't use the thing you just created. So go under Files, and you want to get this thing from Genius Scan. That's our guy. So select it, hit the check mark, and it's in there, and it's named properly and everything. So once all that's good, you hit Submit. If you're not clear about whether you want to use the one you did, you could hit the Save as a Draft thing. But then you should get this sort of success page that tells you, yeah, you did it. You'll also ought to get an email, and that'll contain a receipt of what time you submitted the thing and everything, so that if I mess up, you can come back to me with the evidence that you indeed did submit things on time. All right, back to the rest of the lecture. I hope that was understandable to everybody. Let's actually start talking about some additional math now. Basically, we're going to continue with the study of proof techniques. There's two new things we're going to look at. One is called, I'm not sure if I've got the phrasing right, frankly. Proof by contrapositives is something a lot of people say. I personally think it ought to be proof by contraposition, but I can't find that word in the dictionary. So anyway, it has to do with the contrapositive of a sentence. The other technique is called proof by contradiction, which is one of the sharper tools in our kit. But in order to look at those proof techniques and actually to do some direct proofs and the other style of things we've been looking at, I'm going to also be introducing a bunch of new definitions today. So we'll talk about divisibility. This is sort of a vast generalization of the idea of being even. We'll look at the quotient remainder theorem, which leads to definitions for things called div and mod. These are operators. And we'll look at the floor and ceiling functions, which probably make perfect sense to people. Those definitions are summarized on a handout. Hold on a second. Let's go over to the straight up view, and I'll show you that handout. Let's see. Sorry, I should have had this already loaded up. But on Blackboard, hello, Blackboard, if you locate our course, there is now a couple of new things in the navigation menu on the left. First, hopefully you all saw the online assignments thing. That just has one item in it at the moment, but handouts has a couple of things. I've already given you these physically, the logical equivalences and the argument forms. The new thing is this guy, the definitions of number theory. So, okay, it's a recap. It's got even and odd on there, but it also has some of these new things I was talking about: divisibility, floor and ceiling, and the quotient remainder theorem. And actually, the last thing on there is also sort of a recap. We've talked about what it means to be prime. Cool. So I'll keep that alive. I guess now is the time to go through what those definitions mean and how we notate them. So the first one, divisibility, is something like this. If you have a number d, think of it as a divisor, you write a vertical bar and then the number n. Now, this is something that needs to be really emphasized. This is not saying divide n by d. or d by n. It's not saying divide anything by anything. What it's saying is think about dividing d into n, and if it would come out even, write true for this thing, and write false if it wouldn't come out even. That is, d divides n is either true or false. It's a Boolean. It is not what you mean by actually doing the operation. Let me say that like 2 more times. If I had 3 divides 12, that's equal to true. 3 divides 11, that's a lot of vertical bars there, that's equal to false. The question is, does the first number go evenly into the second number? When I was actually learning this stuff myself, I had a teacher with a southern accent who pronounced the vertical bar like this. I think I may have already told you this joke. Gazinta. We didn't know what the heck he was talking about, but he means goes into, right? 3 goes into 12 evenly. And you see why that's a generalization of the notion of evenness? If you write 2 divides some number, 2 divides 7, well, it doesn't. Right? So 2 divides 7 equals false, but 2 divides, 14, that equals true. So 2 divides x is the exact same thing as saying that x is even. The idea of the divisibility operator is it takes this thing we have for sort of whether a number is divisible by 2 or not and turns it into something that's a more general question, right? Are we divisible by whatever number? Okay, so that's divisibility. Before I talk about floor and ceiling, I think it might be smart to talk about the quotient remainder theorem, which is really closely related to this divisibility stuff. Okay, so what is the quotient remainder theorem? Well, let me put it this way. Back in the day when you did division, you probably learned this in 3rd grade, maybe 4th grade. Let's do an example of a division problem. Suppose I was looking at how many times does 5 go into 23. There would have been 2 parts to the answer. You would have said 5 goes into 20 4 times, and then you multiply it back and get a 20, and then you subtract, and you get this 3 down here. The idea is that when you do division of one number into another, there's always the sort of the even amount of times it goes in, and then there's the what's left over. That's quotient, and that's remainder. We call them Q and R usually. Now, how do you know that you're finished with a long division problem? It's when that remainder is the sort of size this one is, that 5 is bigger than it, right? So what you know is that n is actually, I'm sorry, I shouldn't say n right now, I should say 23 is equal to 4 times 5 plus 3. Notice what I've done there. I was talking about division, yeah, but what I wrote here isn't strictly a multiplication thing. This is an operation with integers. There's no rational numbers here. Strictly a deal with whole numbers. In general, let's talk about the general case. We're thinking about dividing some divisor into a number n. You'll get Q, and you'll get way down at the end, you'll get R. So let me just sort of try to take what we did before and put everything in the same places. It'll look like n can be written as a quotient times that divisor plus a remainder. The problem comes in that this is not necessarily a unique expression. right? You could have, well, let me give you an example. Well, okay, first let me say not necessarily unique. That's bad, right? We usually like in math to have unique answers. But I could do like 23 equals 4 times 5 plus 3. But I could also write 23 is equal to 2 times 5 plus 13. Did I do that right? Yeah, I did. So what do we do? What do we assert to make sure that this is in fact a unique expression? We put limits on what can R be. R can't just be anything. The final result, the quotient remainder theorem, says that n can be written as q times d plus r, and that r has bounds on it. It's got to be a positive number. Well, it can be 0. In fact, 0 is the case when the d divides evenly into n. But the biggest it can be is d. In fact, it can't be equal to d. It's got to be smaller than d. So these bounds on the values that r put create a uniqueness, that q and r are now unique. Can I squeeze that on here? That's important. Okay, so if you look at the statement of the quotient remainder theorem, which I think I took away. Nope, here it is. There it is in the next to the last box. Let me zoom in a little so this is clearer on the video. For all n and d in the integers, we've got to have positive d. Not sure why that is. Oh, well, I guess dividing by negative numbers, you just work it out as if it was positive, and then you take a negative. Anyway, this is a little new thing on here. We've got the existence operator with an exclamation point after it. That means unique existence. It's actually a really common thing that in a theorem you want to create unique integers. So there exists uniquely q and r such that that are in the integers such that n is qd plus r, and those bounds I specified about r. Now, there's some new notation that's written down there. Mod and div. Div and mod, given the other order, isn't it? So what do those have to do? Well, you write n mod d to mean the r that you get out of the quotient remainder theorem. That looks funky, like there's a... Let me try that one more time, a little more space. N mod d. Let's make sure that doesn't look like it's just a long word where I stuttered on the letter D, equals to r. What that means is r is the remainder. Can I just abbreviate remainder from the quotient remainder theorem? Now, let's do a couple of examples. The one you're most familiar with is clock arithmetic. And that is the same thing as working mod 12, unless you're in the military, and then that's mod 24. Clock arithmetic, you can do operations and find the results mod 12 and be, well, let's not worry about operations for the moment. How about we just do an example of reducing a particular number, mod 12. Let me do one that you probably know. 75. Why would I expect you to know that one? Actually, let me write, I should have white out on the screen here. 75 mod 12 equals. Well, there's a multiple of 12 that's right nearby 75. How tall is somebody who's 6 feet tall? Yeah, they're can we see me and see the screen at the same time? I just have to get this thing out of there. Okay. 75 mod 12 is predictable because 72 inches is 6 feet, right? So 72 is a multiple of 12. What does that say about what do we get if we think about 75 mod 12? Turns out the Q is going to be 6, and the mod is going to be 3. Yeah. 75 mod 12 is equal to 3. I just mentioned the other guy, the div. If n mod d gives you the remainder, n div d is going to give you the other piece of that. So if I said 75 div 12, that's the 6 that we get, the 6 feet that goes into 72 inches. So 75 div 12, quotient 75 mod 12, remainder. It's actually often really fairly easy to figure out what a number is, mod anything, so long as you know your times tables well. And if you don't know your times tables well, you can do it with a calculator. So let's do something that's beyond the realm of the times tables. That'll be illustrate how you can do it with a calculator. How about 129 mod 17? All right. So how would I do that using a graphing calculator? Well, do the division. What did I just say? 129 mod 17. So take 129 and divide it by 17. Cool. So you get the answer, but it is a decimal. Well, the div is staring you right in the face. That's the whole number part, the 7 that you see there. So 129 mod divided by 17, or 129 div 17, is going to be 7. The mod is sort of hiding here in the decimals. I shouldn't draw on my calculator screen. Gross. Anyway, I'll come back and erase that or clean that later. 129 div 17 is 7. If we take away the div part, the whole number part, we've got basically something that looks like the mod divided by 17. How can we get back the mod? Just times it by 17. So, see how the answer came out 10? 129 mod 17 is 10. Cool stuff. And you can use your calculator for any of those kinds of things. It's helpful. There are other ways to proceed. There's one other notation that I want to show you for the mod operator, which is that sometimes you do things sort of knowing that a whole bunch of calculations are going to be done modulo the same thing, in which case you kind of put the mod at the end of the line in parentheses, and you use a different version of the equal sign. So another way to write this same thing that I just did would be say that 129 is equivalent to 10 if the operations are done mod 17. So if you see these triple bar equal signs, that's usually means that you're going to have a mod 17 or a mod whatever written at the end of the line. You can't be sure that that'll happen because sometimes there'll be a context that makes it clear we're all doing everything mod 100 or some other number. So sometimes that won't be present. And another third option for this is you could say 129 is congruent with a little 17 subscript. Gets you the same idea. So a bunch of different ways to write it, but the main idea is to be able to use this one, that a number mod another is equal to a third. All right, do I have enough screen time left to talk about the last definitions, the floor and the ceiling? Sure, why not? Let's get a new sheet of paper. And what floor and ceiling mean is just, floor and ceiling mean rounding, either up or rounding down. So floor is round up. Just said it wrong. It's down, round down, like the floor is below us. I should have thought of that. Ceiling means round up, Got an I in there, doesn't it? And both of them do nothing if you've got a whole number, so they don't move you at all. You do need to think about these in terms of the number line. Like if I have a number line here, with some zeros right there, here's 1, 2, 3, pi, for instance, would be right about there, yeah? If I do the floor of pi, it's going to move me down in the numbers to 3. But if I had a number like, how about right about here would be negative 1.6. The floor of that rounds down, so it goes to minus 2. That is, floor moves us to the left on the number line. And ceiling is going to move us to the right on the number line. So I wonder why we always say up or down. Maybe we should say left or right. Perhaps it's thinking about that as the y-axis instead of the x-axis. I don't know. How do we notate these things? The floor is usually drawn by writing braces that have little foots on them at the bottom. So the floor of x would be written like that. The ceiling of number would be written with the little dashes or the little square hooks on it at the top. So that I think that notation is evocative of what we're doing here, taking x down to the next whole number or moving it up to the next whole number. Let me give you the definitions for these while we're here. They were on that sheet, but I might as well write them out. Floor of x is equal to y if and only if. There's two things we're going to need. One is that y's got to be an integer. And the other is that it's sort of the right integer. We want y to be smaller than x, possibly equal to x. If x is, in fact, a whole number, it will be equal. But you know what's definitely bigger than x? The next number up, y plus 1. Right? Now, what can we write for the ceiling? It's very similar. The ceiling of x is equal to y if and only if, again, y's got to be an integer. Oh, I noticed last one I forgot that I put a comma instead of the and sign. We want that to be an and there. Again, y is an integer, and now how will the inequality look here? Now we want y to be the next number bigger than x, except that it might be equal to x. So we'll have the potential for equality at the high end, and the number that's definitely smaller than x will be y minus 1. Sorry, I had to crowd that in there, but they're written with more clarity on the handout that I had viewable over here. You can see there's floor of x if and only if it's all the same stuff. Okay. All right. So we talked about quotient remainder. We talked about ceiling and floor. I guess before I go too much further, I better give you an example of those things. What's the floor of 4.99? Everybody? 4, right? What's the ceiling of 4.99? That's 5. What's the floor of negative 17? Right, because that's a whole number, it is negative 17. And similarly, if I took the ceiling of it, it'd be negative 17. If you've got a whole number, neither of these things change anything. But if you've got something that ends with something in the decimal places, then it does move it. I want to point out something that you might not believe at first, but if I said 4.9 with a line over it, that means the 9's go on forever and ever. Do you know what the floor of 4.9 with the 9's going on forever is? Strangely, this is 5, because that number in there is actually equal to 5. We'll see why that's true a little bit later in the course. Okay, so let me go back to our slides. Did I close our slides? I think I did. No, I didn't. There it is. So what about these two proof techniques I was talking about? The method of contraposition. Here's how you do it. you're going to state the theorem as a universal conditional sentence. That's not hard. Then you're going to figure out the contrapositive of that universal conditional sentence. That's not hard. That's what the contrapositive means. If you have P implies Q, its contrapositive is knots on the pieces and the order switched, right? Not Q implies not P. And then you're just going to do a direct proof like we've done before for the contrapositive, meaning you'll assume that not Q is true for a particular but arbitrarily chosen X, and then you will try to deduce that not P is true. I'm not quite clear on why this is traditionally thought of as an indirect argument technique, because it literally is direct. You just are proving the contrapositive instead, but we know that those are logically equivalent. So, but anyway, people do call this an indirect method. Technique is called contradiction. I'm not sure about this statement here. Some people are suspicious of proofs by contradiction. I think not so much anymore, but historically mathematicians were a little skeptical about proofs by contradiction. Certainly it's the case that if you could find a different way to argue, if you could find a proof that was direct instead, it would certainly be considered better. But it's really an accepted argument technique now, and it's been accepted for quite a while. In fact, it goes back to ancient Greece. So here's how the outline works. You do something a little perverse. You start out by assuming the statement you want to prove is actually not true. It's a false statement. And then from there you argue, but you have to argue in this weird alternate universe where you think the statement that you actually believe is true is false, right? And you argue with a perverse goal in mind. You argue so that you eventually reach something that's literally impossible. Okay, why is that good? Well, if the assumption that the original statement is false ends up being equivalent to a contradiction, it's always false. That's like a double negative, right? It's false that the thing is false. So what must actually be the case is the original statement is true. Yes, in ancient times it was referred to by this Latin phrase, reductio ad absurdum, meaning literally reduction to an absurdity. All right, so we'll do a quick example. Actually, it's funny that these two different proof techniques can usually be used almost interchangeably. If you can develop a proof by contradiction of something, you can often figure out a way to do a proof of it by contrapositives and vice versa. So the example I have in mind was something we already did, was show that if you know x is even, then its square will be even. In fact, x squared would be divisible by 4 in that situation. So what's literally true is there's an if and only if relationship between x being even and x squared being even. But the presumption here is that x is an integer. So we've already done the if part. We just need to handle the only if piece. That is, this is what we need to make a proof of. The universally true, universal conditional sentence for all x in z, x squared even implies x is even. Okay, so look, think about it. If you try to prove that, you're not going to get far, because what's the hypothesis going to be? Let me just speak the way the proof would start out. You'd say, suppose x is a particular but arbitrarily chosen integer such that x squared is even. So great, you get to use that x squared is even, and that means x squared can be written as 2k for some integer k. But where is that going to help you in getting that x is even? It's not going to work out so good, because if you try to get x out of the expression here where x squared is 2k, you're going to need to take a square root, and that's going to mess things up entirely. You'll have root 2's and square roots of k's. It'll be ugly. So, recognizing that it'll be ugly, you try the method of contraposition. Let me bump out of that, and we'll do some writing. So what would the contrapositive of that statement be? It would be that for all x in the integers, if x is not even, so x is not even is the same thing as saying x is odd, that should imply that x squared is not even. In other words, x squared is odd. And while the original statement was ridiculous, we couldn't figure out anything that would allow us to prove that, this is really easy to prove directly. Do you see how it's going to fly? You assume x is a particular but arbitrary integer such that it is odd. I'm just going to start being more brief now and just assume x is odd. Then x looks like 2k plus 1 for some integer k. And then it's really easy to see that x squared is going to be odd. In fact, I almost feel like we've done this problem before. Then x squared is equal to 2k plus 1 squared, which is equal to, make sure you FOIL roll to get all the terms of that thing. It's going to be 4k squared from first times first. And then there's a 2k and another 2k from the outer and inner terms. So that's a total of 4k plus 1. And then let's just factor or play with that until it looks like the definition of an even number. Oh, excuse me, of an odd number. It'll be 2 times 2k squared plus 2k plus 1. Great. So since 2k squared plus 2k is an integer, it follows that x squared satisfies the definition of odd. Oops. And that's what we're after, right? So that's your QED moment, right? You have shown that if you assume x is odd, it gets you that x squared is odd, and that means the contrapositive statement that if x squared is even, x will be even, is true. Okay, so the next proof I want to do by the other technique, proof by contradiction. So let's talk about what that is. Also, this proof we're going to be dragging in one of the new definitions. So that went by a little quick before. I just kind of showed you the sheet. But here's the formal definition of when d divides n. So on the left of the if and only if symbol, you see d divides n, which is exactly how you want to read that. Just pronounce the vertical bar like the word divides. D divides n if and only if there exists an integer k so that n equals dk. I want to point out this is somewhat similar to the scenario with the quotient remainder theorem, where you've got a statement that's about divides, and you don't use divisibility or division to define it. You instead use multiplication. That's really important that we end up using the arithmetic of the integers to help us know when one thing divides another. So it's written in terms of times. Great. Okay, so the theorem I'd like us to attack is a little bit of an odd one, and it involves that definition we just did. It's universal for all x in z, but also universal over divisors. So for all x in z and all positive d in z, d does not go into x squared implies d does not go into x. Let me point that out, that funny notation for the negation of the divides operation. It's the vertical bar with a little slash through it. But that stuff up above means exactly what's written here in English. For all integers x and all positive integers d, if d does not divide x squared, then d does not divide x. Oh, what is the contrapositive of that? Yes, exactly. Well, no, I'm just kidding around. So it's quantified the same way, and what we do is negate the bits. So just take away those little slashes. and reverse the direction. Before it was x squared going to x, now it's x going to x squared. If you were to say that in words, it would be for all integers x and all positive integers d, if d divides x, then d divides x squared, which probably sounds pretty logical. Okay, so you could go with that. You could take that contrapositive statement and just prove that, but I did want to illustrate the other technique, so we're going to be doing this one by contradiction. Here goes. The theorem is for all x and z, for all d positive in z, d divides x implies d divides x squared, equivalent to the thing I started with, right? That's the contrapositive. Suppose not. Those words are always the first sentence in a proof by contradiction. You just say, suppose not. What does it mean to suppose not for this? Well, think about the negation of it. Remember that the negation of an if-then is an and statement. So it'll be the if and not the and. And it's interesting to note that if you started with the contrapositive or the original statement, when you put it through that ringer, find the negation, you get the same thing, which is kind of another way to think that about the statement and its contrapositive being logically equivalent. They're both negations of the same thing. Okay, so back to the proof. Suppose not, then there are integers x and d with d positive such that d divides x and d does not divide x squared. Get it? The same quantifiers or different quantifiers? Oh yeah, this was for all. The negation of a for all exists. So there are integers. And then the if part and not the then part. D divides x and d does not divide x squared. Great. So since d divides x, there is an integer k such that x equals dk. Where'd that come from? That was the excuse me. That was the definition of divisibility. Okay, so that's really a very useful little step in a proof. When you've got a supposition, you don't know where to go. Try writing down the definition of the thing you're supposing. So then, where do we go from that? Try figuring out what x squared looks like. Just substitute dk in where x squared is, because, like I said before, x is equal to dk. X squared will be dk squared, which is d squared k squared. We can factor a d out of that mess, and you get d times dk squared. That's the tail of this sentence is just justifying why we could do it, say, by substitution in basic algebra. Therefore, d divides x squared, because dk squared is an integer. Thus, d divides x squared, and wait a minute, also d does not divide x squared. That was one of our assumptions. So, that's a contradiction. If you've got a statement and its negation, that's a contradiction. So, our original assumption is false, and the theorem is true. It's a nice, pithy little proof by contradiction. Okay, well, that'll be it for today. I'll ask you to take a look at the worksheet on Blackboard and have at it. And if you haven't figured out yet how to get onto WebEx and join me, now's the time.